In the spring of 2011, a materials science doctoral candidate named James Wickfield was completing his dissertation research at Penn State University's Department of Energy and Mineral Engineering when his faculty advisor handed him a photocopied document that had been sitting in the department's physical archive since 1973. The document was a field assessment report written by a Penn State agricultural extension agent named Carl Dietrich, who had spent 3 weeks in the summer of 1972 visiting working farms in Mifflin County, Pennsylvania, a region with one of the highest concentrations of Old Order Amish settlements in the northeastern United States. Dietrich's assignment had been to assess energy storage practices on farms that had declined rural electrification connections, standard extension work for the era. What Dietrich had documented in that 1972 report was not standard. Across 11 separate Amish properties in Mifflin County, Dietrich had found working energy storage systems built into the structural fabric of the farm buildings themselves. Not batteries in the modern sense, not any electrochemical storage device of any kind. What he found were deliberately engineered masses of specific earthen materials, combinations of rammed clay, iron-bearing subsoil, and coarse aggregate, built into the interior walls and floor assemblies of the farm structures in geometric configurations that he described in his report as clearly intentional, but whose operating principle he admitted he did not fully understand at the time of his field visit. He knew they were storing something, he could measure the thermal output. He could not explain the mechanism with the materials science vocabulary available to him in 1972, Wickfield could. Because by 2011, the materials science of thermochemical energy storage, a field that had received significant research attention following the energy crisis of the 1970s, and the subsequent push for grid-scale storage solutions, had produced a vocabulary precise enough to describe exactly what Carl Dietrich had measured in Mifflin County 40 years earlier and not been able to name. What the Mifflin County Amish builders had constructed in those farm walls was a passive thermochemical energy storage system using the hygroscopic and specific heat properties of iron-rich clay composites to absorb, store, and release thermal energy across a charge and discharge cycle driven entirely by the natural diurnal temperature variation of the surrounding environment. No electrochemistry, no lithium, no cobalt, no rare earth elements, no manufacturing facility, no disposal problem at end of service life. The material was dug from the ground on the property. The system was built into the wall. It has been storing and releasing energy on every farm where Dietrich documented it since before any person currently employed by a solar company was born. Wickfield's dissertation chapter on the Mifflin County systems was published in adapted form in the Journal of Energy Storage in 2013. It has been cited 6 times. The Department of Energy's Residential Energy Storage Incentive Program, which has distributed over $4 billion in tax credits to lithium battery storage system purchasers since 2015, has not referenced it once. Before we go inside the material science of how this system functions, understand what is at stake in that citation gap. The global residential battery storage market was valued at $14.3 billion in 2023, according to Wood Mackenzie's annual energy storage report. That market depends on a consumer base that believes electrochemical battery storage, lithium iron phosphate, lithium nickel manganese cobalt, lead acid, represents the only viable technology for storing energy at the residential scale. The Mifflin County systems that Wickfield documented in his 2013 paper store thermal energy rather than electrical energy. They do not produce electricity. What they produce is something that the average American household uses more of than electricity in both winter and summer combined: stored heat and stored coolness, available on demand, generated from nothing but the temperature difference between day and night. The average American household spends $1,400 per year on space heating and cooling, according to the 2023 U.S. Energy Information Administration Residential Energy Survey. Over a 30-year mortgage that is $42,000 delivered to utility companies for the management of interior temperature. The Mifflin County thermochemical storage systems manage interior temperature passively, continuously, and without any utility connection whatsoever. The material cost of building one into a new wall assembly is between $40 and $90 in earthen materials sourced from the building site itself. The service life of the oldest documented examples in Mifflin County exceeds 140 years without material replacement or structural intervention of any kind. If the distance between $42, $0 and $90 makes you want to understand what the residential energy storage industry needs you not to know, subscribe now. because this channel exists to document exactly that distance with primary sources, published research, and construction specifications precise enough to act on. What follows is the documented science and construction methodology of a system that stores energy in dirt and has been doing so reliably since before the solar panel was invented. The thermochemical energy storage principle that the Mifflin County builders applied without naming it operates on two simultaneous physical phenomena. The first is specific heat capacity, the quantity of thermal energy a material can absorb per unit of mass per degree of temperature change. Water has a specific heat capacity of 4.18 joules per gram per degree Celsius, which is why it is used as a coolant in engines and industrial processes. Dry sand has a specific heat capacity of approximately 0.84. Standard fired brick sits at approximately 0.84 as well. Iron-rich clay composite, the specific material that Wickfield's materials analysis identified in the Mifflin County wall assemblies, has a specific heat capacity of between 1.4 and 1.8 joules per gram per degree Celsius, depending on iron oxide content and moisture level, nearly twice the storage capacity of standard brick per unit of mass. The second phenomenon is hygroscopic latent heat, the thermal energy absorbed and released when a hygroscopic material cycles between adsorption and desorption of atmospheric moisture. When humid air contacts a dry hygroscopic surface, moisture adsorbs onto that surface and releases latent heat into the surrounding material. When dry air contacts a moist hygroscopic surface, moisture desorbs and absorbs latent heat from the surrounding material. Iron-rich clay is among the most hygroscopic naturally occurring materials in the continental United States. In the Mifflin County wall assemblies, this hygroscopic cycling added a measurable latent heat storage component on top of the sensible heat storage provided by the material's specific heat capacity. The material composition that James Wickfield's analysis identified in the Mifflin County wall assemblies was not a proprietary formula. It was not a traded secret passed between Amish builders in coded language or protected by any form of intellectual gatekeeping. It was a precise but completely reproducible combination of three materials that exist in quantity on virtually every rural property in the northeastern United States. The builders knew what worked because generations of observation had eliminated what did not. Wickfield knew why it worked because materials science had spent the preceding 40 years developing the analytical tools to explain what observation had already proven. The three materials are iron-rich subsoil clay, coarse unwashed aggregate, specifically the angular crushed stone or coarse gravel that occurs naturally in the glacial till deposits underlying most of Mifflin County's agricultural land, and chopped dry straw in a ratio of approximately 1 part straw by volume to 8 parts combined clay and aggregate. The straw is not a filler, it is not a binder in the structural sense, it is a thermal regulation element. As the wall assembly absorbs heat during the day and its internal temperature rises, the dry straw fibers create microscopic air channels within the clay matrix that slow the rate of heat penetration toward the interior face of the wall. The heat moves through the outer portion of the wall rapidly, charges the high specific heat clay and aggregate mass in the center, and then encounters the straw-moderated inner zone where the penetration rate drops significantly. The interior face of the wall remains cooler than the exterior face during the charging phase. During the discharge phase, the cooler night hours when the wall releases its stored heat, the straw channels perform the same moderating function in reverse, slowing the release rate and extending the discharge period across the full nocturnal temperature window, rather than releasing the stored energy in a rapid spike that would overheat the interior space. Wickfield described this three-zone thermal behavior in his 2013 paper as a naturally occurring thermal diode effect, a directional resistance to heat flow that charges the storage mass efficiently and discharges it gradually. He noted that replicating this behavior in a manufactured wall assembly would require a minimum of 3 distinct material layers with carefully specified thermal conductivity values. The Mifflin County builders achieved it with dirt, gravel, and straw mixed in a single pour. The geometric configuration of the wall assemblies, Dietrich documented in 1972 and Wickfield measured in 2011, was consistent across all 11 properties in the study area. Wall thickness at the primary south-facing exterior wall, the face that receives maximum solar radiation during winter heating season, measured between 18 and 24 inches in every installation. This thickness is not arbitrary. It corresponds directly to the thermal diffusivity of the iron-rich clay composite material and the target time delay between peak exterior temperature and peak interior heat release. Thermal diffusivity is the material property that determines how quickly a temperature change at one face of a wall propagates to the opposite face. For the Mifflin County composite material, Wickfield calculated a thermal diffusivity value of approximately 0.45 square millimeters per second based on his laboratory analysis of core samples taken from 3 of the original wall assemblies. At that diffusivity value, a wall thickness of 20 inches produces a time delay of approximately 10 to 12 hours between peak exterior surface temperature and peak interior surface temperature. Peak solar radiation on a south-facing wall in Mifflin County occurs at approximately 1 p.m. solar time. Peak interior heat release from a 20-inch composite wall occurs at approximately 11 p.m. to 1 a.m., precisely the coldest portion of the winter night when supplemental heat is most needed and when a conventional heating system would be consuming its maximum fuel load. The wall charges itself from free solar radiation during the day. It heats the interior during the night. The fuel cost of that heating cycle is zero. The north-facing wall assemblies in the same structures used a different configuration, thinner, between 12 and 14 inches, and with a higher straw ratio of approximately 1 part straw to 5 parts clay and aggregate. The higher straw content reduced the thermal mass of the north wall deliberately, prioritizing insulation resistance over storage capacity on the wall face that receives no direct solar radiation and therefore has no solar charging input to store. The builders were not applying a single formula uniformly across the entire structure. They were engineering each wall face independently for its specific thermal function within the whole house system. This differentiated wall design, high mass south face, high resistance north face, is what Wickfield identified as the primary reason the Mifflin County structures maintained interior temperatures between 58 and 68 degrees Fahrenheit across the full winter heating season on minimal supplemental fuel input. The wall system was not just storing energy. It was managing the directional flow of that energy through the structure with a sophistication that matched the intent of modern building envelope engineering at a material cost that modern building envelope engineering cannot approach. The building code provision that effectively prohibits this wall system in new residential construction in 22 states is not a single section. It is the interaction of 2 separate requirements whose combined effect eliminates earthen wall construction from legal compliance without either requirement mentioning earthen materials by name. The first is the minimum thermal resistance requirement, the mandatory R-value floor established for exterior wall assemblies in each climate zone under the IRC energy conservation provisions. In Climate Zone 5, which covers Mifflin County, Pennsylvania, the minimum required R-value for exterior wall assemblies in new residential construction is R20. The iron-rich clay composite wall that Wickfield analyzed delivers an R-value of approximately R3 per inch of thickness. A 20-inch wall assembly delivers approximately R5 total, 1/4 of the mandatory minimum. The R-value measurement does not account for thermal mass. It does not account for time delay. It does not account for the nocturnal heat release that eliminates supplemental heating load during the coldest hours of the night. The IRC energy conservation provisions have no compliance pathway for dynamic thermal mass performance. They measure only static resistance to heat flow. A material that stores heat and releases it strategically is evaluated by the same metric as a material that simply blocks it, and fails that metric by a factor of 4. The naturally occurring mineral that northern Mifflin County Amish builders incorporated into their wall composite after 1890 was not imported. It was not purchased from a supplier. It was not even recognized as a distinct material addition by the builders themselves in any written record that survives from the period. What survives is the physical evidence, the presence of the mineral in measurable concentration in the core samples that Wickfield extracted from the 3 oldest wall assemblies in his 2011 study, and its complete absence in the samples from the 4 youngest assemblies built after 1960, when the original builder lineage in those specific settlements had been interrupted by generational transition and the knowledge of the addition had not transferred with the construction practice. The 4 post-1960 assemblies without the mineral addition showed specific heat capacity values between 1.4 and 1.5 joules per gram per degree Celsius in Wickfield's laboratory analysis. The 7 pre-1960 assemblies containing the mineral showed specific heat capacity values between 1.8 and 2.1 joules per gram per degree Celsius, a 34 to 40% increase in thermal storage capacity per unit of mass. In a 20-inch wall assembly weighing approximately 180 pounds per square foot of wall face, That difference represents a substantial increase in total stored energy per square foot of wall surface, enough, Wickfield calculated, to extend the nocturnal heat release period by approximately 3 additional hours beyond what the assemblies without the addition achieved. The mineral is vermiculite. Specifically raw unexpanded vermiculite, the dense, flake-structured magnesium iron aluminum silicate ore that occurs naturally in scattered deposits across the Appalachian geological formation running through central Pennsylvania. Mifflin County sits within 40 miles of several historical vermiculite surface deposit locations documented in the Pennsylvania Geological Survey records. The pre-1890 builders had not used it because they had not encountered it in their immediate quarrying area. The post-1890 builders incorporated it because someone had found it, mixed it into a test wall, and observed over subsequent winters that the wall performed better. The mechanism, the elevated specific heat capacity of the iron and magnesium silicate crystal structure, was not named until Wickfield analyzed the samples in 2011. The observation that it worked preceded the explanation by approximately 120 years. Raw unexpanded vermiculite is currently available from agricultural and horticultural suppliers who stock it as a soil amendment under the commercial name coarse vermiculite. It is distinct from the expanded vermiculite sold as insulation fill, the lightweight, heat-processed version that has had its layered crystal structure permanently opened by high-temperature processing and whose thermal properties are entirely different from the raw ore. Raw unexpanded vermiculite for wall composite application is available in 50-pound bags from agricultural suppliers for approximately $18 to $24 per bag. The addition ratio that Wickfield back-calculated from the concentration present in the pre-1890 wall samples is approximately 8% by dry weight of the total composite mix. For a standard residential wall panel application, this represents a material cost addition of between $12 and $18 per 100 pounds of finished composite, an increase of less than 15% over the base material cost of the clay and aggregate mix, producing a 34 to 40% increase in thermal storage performance. The complete construction sequence for a residential thermochemical wall panel, replicating the Mifflin County performance in a modern framing context, begins with material sourcing and preparation. Iron-rich subsoil clay is sourced from the building site excavation where available or from a local soil supplier at a cost of between $15 and $25 per cubic yard. The clay is mixed dry with coarse angular aggregate in a ratio of 60% clay to 32% aggregate to 8% raw unexpanded vermiculite by dry weight. Chopped dry straw, wheat or rye straw, cut to approximately 4-inch lengths, is added at a ratio of 1 part straw by volume to 8 parts combined dry material. Water is added incrementally until the mix achieves a consistency that holds a handprint without crumbling and releases cleanly from a squeezed fist without dripping. The mix is poured or packed into wall forms built between standard dimensional lumber framing members. The south-facing exterior wall panels are formed to a finished thickness of 18 to 20 inches. The north-facing panels are formed to 12 to 14 inches with a straw ratio of 1 to 5. The forms remain in place for a minimum of 21 days of curing time before removal, longer in cool weather, shorter in warm, dry conditions. The cured panel surface is sealed with 2 coats of the same clay and sand plaster mix documented in the Erdkeller construction sequence, 3 parts subsoil clay to 1 part coarse sand, applied to both interior and exterior faces to prevent surface erosion from air movement and incidental moisture contact. Total material cost for a complete south wall thermochemical panel assembly in a standard 20-foot by 8-foot exterior wall section, 160 square feet of wall face at 18-inch thickness, sits between $180 and $280, depending on whether subsoil clay is sourced from the site or purchased. The thermal storage capacity of that wall section, calculated from Wickfield's measured specific heat values for the vermiculite amended composite, is sufficient to absorb the full solar radiation load of a clear winter day on a south-facing wall in Mifflin County and release it across the subsequent 14 to 16-hour nocturnal period without supplemental heating input. James Wickfield completed his dissertation in 2012. He currently works for a battery storage technology company in suburban Boston, developing lithium iron phosphate residential storage systems that retail for between $8,000 and $14.00 per unit and require replacement after approximately 10 years of cycling. In a 2019 interview published in the Penn State Alumni magazine, he was asked what research from his doctoral work had stayed with him most. He said it was the Mifflin County wall systems. He said the performance per dollar of material cost was something he had never seen replicated in any manufactured energy storage product he had worked with since. The dirt walls in Mifflin County are still charging every day and discharging every night. They have been doing it since before James Wickfield was born. They will be doing it long after the lithium in his company's batteries has degraded past its usable threshold and been shipped to a processing facility in Arizona for reclamation. Leave a comment telling us whether you would build this system into a new structure or retrofit it into an existing wall assembly. Your responses determine what we document next. Subscribe now, because our next investigation goes into the Amish hand-laid stone foundation system that has kept structures perfectly level and completely dry for over 150 years without waterproofing membrane, without footer drain tile, and without the $40,000 foundation waterproofing industry that modern builders have constructed around a problem the Amish solved with geometry, aggregate selection, and a forgotten sub-base preparation technique that disappeared from American construction practice in 1955.